And then later on, after we figured out there were electrons, that electrons are actually flowing the other direction. And at that point, they said, we're not changing that. So current flows from positive to negative. Closer to reality is electrons are moving in the opposite direction. Some textbooks, and I can't remember if yours does it or not, some textbooks will talk about electron current. I'm not a fan of it, but it's the current of the electron flow as opposed to the standard current flow.
Is that why it's upstream?
Say it again?
Is that why it's upstream, I guess?
Yeah. Yeah.
Interesting.
All right, so let's play around with electrons here, or with, suppose I have a positively charged plate. Let's assume it's huge charged plate. What is the formula for the electric field at this point right here?
No.
And we do this Friday. I guess I should, instead of writing Q there, let me write. It has a positive sigma. There's a uniform charge density, positive charge density, surface charge density.
So it's a positive charge.
It's a positive charge, it's just I'm using sigma as the charge density, surface charge density, as opposed to what the absolute charge is.
What about do you use that?
I want to know, what is the electric field there?
Is it lambda over 2 pi r?
That's if I have a infinite line of charge, we're talking about a plate of charge. It's the one we did after that.
Oh, lambda equals 3.
Lambda equals
The
13.
finite one.
No, we're dealing with assuming an infinitely large plate.
Sigma over 2
Epsilon.
Epsilon 0, or what do you call that? Epsilon.
Epsilon sub naught or epsilon sub zero, whichever one. All right, so the electric field here is sigma over 2 epsilon sub naught if it's free space. If I got something sitting there, it will be something different. It'll be just epsilon. But right now, let's just assume there's nothing there. The vacuum of space. And over here, it's sigma over 2 epsilon sub naught. Why did I draw the arrows that way?
Perpendicular to the surface.
Okay, that's one reason. Why didn't I draw the arrows flipped around though?
Since it's a positive charge, it's going to.
Absolutely. All right. So now I introduce a second plate, infinitely large. This has a charge of negative sigma. So I'm just going to extend these lines here. I mean, the blue electric field lines. If this plate is indeed infinitely large, then these electric field lines go on forever. But now let's take a look at the red. What is the electric field at this point in the middle because of the red plate? All right, so you're saying it should go like that?
Yeah, it's gonna go towards the red clear,
Why?
because it's negative.
Yes. All right. So I have this electric field going like this. What's the magnitude of this?
Is it going to be
The negative is a directional thing, so given that we've already established direction this way, the magnitude would be sigma over 2 epsilon naught. Officially, if we had the arrows pointing, the red arrows pointing the opposite directions, then we can throw the negative in, which just means, oh, they're going this way. So we have sigma over 2 epsilon sub naught and sigma over 2 epsilon sub naught. Therefore, let's get rid of. All right. So therefore, I have these three regions right here. What is the total electric field in each of the regions? So what about out here? We'll call this region 1, region 2, and region 3. In region 1, what is the total electric field? Zero. How'd you get 0?
You have like one part of the electric field going that way, and the other going this way, so it's like a cancel.
What about region 3?
Also 0.
What about in the middle?
Is it gonna be sigma over epsilon sub naught?
Yep. Because I have two electric fields going in the same direction, so I'm just adding them up. All right,
So the
Wow.
two,
Jalissa.
so why did you get rid of the two, or if you're adding it up, why did it one?
When you add it, you got sigma over 2 epsilon sub naught plus sigma over 2 epsilon sub naught, which is 2 sigma over 2 epsilon sub naught. 2's cancel.
That was my question.
Okay. So what we have here, if I have these two infinitely large plates that are of opposite signs but the same magnitude of charge but opposite signs, then the electric field on the outside is 0, but the electric field in the middle is sigma over epsilon sub 0. Again, I'm working under the assumption that one of them is positively charged, the other one is the negative of whatever that is. So if I take these two plates here, and this is 10 microcoulombs per square meter, and this is negative 10 microcoulombs per square meter. I'm establishing that this is positively charged and that's negatively charged. What is the direction of the electric field in the middle? Okay, I saw a couple fingers in that direction. I'm assuming that the 4 is a groundswell. And the magnitude of it, well, it's 10 times 10 to the negative 6th divided by epsilon sub naught, 8.85 times 10 to the negative 12. One point times 10 to the 6th. About 1.2. Apparently it's changed his mind. So we'll go with this right now. Units?
Newton coulombs. Newton per coulomb. Sorry.
Newton per coulomb.
So, what'd you get? I just get times 2. It's the same.
Yeah, it is the same thing.
All right, so other questions before I talk about the assumptions we made and where we can relax on those?
Do we need to commit numbers like the epsilon value to memory? Or
It's one of those things that'll be on the top of the quiz or top of the first page of the test, but it's good to know. But if you're having a moment and blanking, it's there. Or if I forget to put it down, just ask. Other questions right now? All right, so this idea of having two plates here that are infinitely large, obviously, it's unrealistic, but we get pretty darn close if the gap between them is small compared to the actual size of the plates. So if this is a S by S, so assume it's a square, and this is also S by S, and this distance here is D, then if D is much less than S in the middle, assume infinite plates. In the lab you're going to be doing next week, you're going to get some sense of how accurate that is. You're actually going to have the plates which are not next to each other. They're going to be about this far apart. And you'll basically start mapping out equipotential lines and then the electric field. That's a comma there. This parallel plates, this is the essence of a capacitor. It's known as a parallel plate capacitor. Now, if I made those plates more flexible, so I've made it some sort of metal foil, and then sort of got them really close to each other. Now, I can't have them touching each other. If there's no space in between them and I just touch them like that, then it's just, I have a conductor. I have two conductors here. Charge is basically going to go right through it. So it's not a capacitor anymore, or it's a broken capacitor. But if I take a capacitor and I put something in between them so that they can get really close together but not actually touching. And it could be as simple as paper. I put paper in between them. Paper is not a conductor. Then I can start to roll it up. And you get things like this. This is a large one. But this is a capacitor right here. So it's just basically two plates that are rolled up with an insulator in between. If we're looking at just the two plates, and this is the lab that you'll be doing in, not next week, but the week after, so 2 weeks and change. You get these two plates here, you can get them really close to each other, and so start measuring capacitance there. And so what we'll do is start looking at the capacitance here, and then start separating them. And we'll eventually find what are known as dielectric constants, which we're about to get to. All right, so I have some potential difference between it. Between these two plates, which plate is a higher potential? Pardon?
Is it higher potential?
Yes, which has a higher potential? Yeah. Just like a battery, the one with the positive charges on it has a higher potential. Negative charge is the lower potential. So if I'm going from here to here, so I'm going from the positive plate to the negative plate, do I have a negative voltage or a positive voltage?
Positive.
All right, I heard both answers, so it is one of those. Let's hoping for someone to make a convincing argument.
It's positive.
Why? Make a convincing argument.
Wouldn't it be negative? Is it
Because
Then you make a convincing argument.
going from 10 to 2, you go -8, right?
Wait, where'd you get mine saved?
Well, if you go like, so you go to a positive to a negative,
Okay.
And so if the, like, say the higher potential is like 10, and say then negative potential is like negative 2, and then go from 10 volts to negative 2 volts is negative 12.
So this one would be negative.
So it'd be negative.
Be careful, it's actually not negative 20 here, because this is not coulombs here, it's microcoulombs per square meter. So we'll get into how to figure the actual voltage out in just a moment, but right now, just the concept. If I'm going from the positive plate to the negative plate, higher potential or lower potential? Is my voltage positive or negative going this way?
Negative.
It is negative. If I'm going in the other direction,
Positive.
all right. So, if I take two parallel plates and I connect them to a battery. Now, when it comes time to writing it, when I drew the battery before, I drew the rectangle with a little nub on top, but this is too much for physicists to write. So they came up with a shorthand for batteries. Now, what I'm about to do, purists are going to argue that it's not a battery, it's actually a power cell. I will talk about that in just a moment. But the symbol that I use for battery and for power cell is that. Now, one of them is a positive side, one of them is a negative side. Well, if you think about it, a plus sign takes twice as much ink as the minus sign, so the one that takes more ink is the positive side. That's the positive side, that's the negative side. Sorry?
This is odd to me. Just draw rectangles.
Yeah. All right, now, the purists will go, that's not a battery, that's a power cell. A battery has to have at least two. So sometimes you will see in textbooks and so forth, they'll do the battery like that, or they'll put a third one in there, or however many power cells are actually being used. Those are distinctions I take off for other things, not that. So officially, this is a battery, and this is a power cell. However, to me, that's also a battery. Occasionally, I do have a student who has been dealing with stuff long enough that he objects to my shorthand. Now, the symbol for a capacitor is two parallel lines. Usually, if this were doing a circuit diagram, it would be, I would draw it like that. Notice that the capacitor has two lines of equal size. The battery has two lines of different sizes. However, for what I'm going to do, I'm drawing them big. So this is the capacitor, and this is the battery. All right, so I got my plus sign and my minus sign of my battery here. Think about what the electrons are going to do. As soon as I connect the circuit here, I have an electron that's going to be leaving here, because electrons hate each other, now it has a path away. So I have an electron that's going to be leaving here. And the electron's eventually going to make its way up to the plate and sit on the plate. Then the next electron's going to come along and sit on the plate. But think about that. As soon as I have an electron sitting on the plate here, this is negatively charged, and so it's going to push electrons away from this plate over here. So for every electron I get on this plate, I should get one leaving this plate. And so when I charge the capacitor, this will have some negative charge, this will have a positive charge. Together they neutralize, but separated they'll hold the charge up to a certain extent. So for every electron I have here, one is chased away from here. But also recognize it gets harder and harder to put electrons onto this plate. Because once I get an extra electron on the plate, it's now negatively charged, and so it's a lot harder to get a second one on. So this struggle here, you'll have electrons pushing from this end and electrons pushing from that end, but at least these are spread out. And so we can start building up charge on this one. But it does get harder as you go. It takes more work to put an electron onto this plate. It is similar, there are some differences, but they're similar to when you're charging a phone. It will strip the electrons off, but once this is neutral, I can start stripping electrons off, but it gets harder and harder to push electrons through. And so when you charge a phone, it will charge a lot quicker at the beginning, and then it will start leveling off. It will never be 100% in reality, it just gets close enough for the phones to go 100%. But this is why if you overcharge a phone, this is the amount of, if you think about this as the amount of energy it takes to charge the phone, it takes a lot more energy to get those last couple of percent than it does the first couple of percent. It takes a lot more energy at the end than it does at the beginning. So once I get them charged, I have this electric field now in between, going from the positive to the negative. I know that electric field is equal to the surface charge density divided by epsilon, so not right now, because I have nothing in between the plates. And sigma is just the charge divided by the area of the plates. Just Q over area epsilon sigma. Now the voltage involved here, there's a rule I need to introduce. I think the book introduces in chapter 20, but I want to introduce it now. And we'll start with the concept of that we had before, where that's 4 volts, 3 volts, 2 volts. I have some sort of configuration of charges which produces that. If I start here and end up here, what's my voltage?
-1.
All right, if I go from here to here,
-2.
if I go from here to here,
0.
does the path matter?
No.
All right, so if I start here, and I go around and I end up back in the same spot, what's the voltage between this and itself?
0.
0. So whatever voltage I gain going across the battery, I have to lose it somewhere because I have to get back to 0. So I get a plus going this way, I'm going to have to lose going this way. It is a negative change in potential. It's a negative voltage because I'm going from positive to negative. So if this is a 12 volt battery, I'm going to gain 12 volts going this way. I have to lose 12 volts going that way. So while this is hooked up to a battery, the voltage is set by the battery. For there. Let's make sure I don't go too far astray. All right. If I put an electron here, what's going to happen to it? I put it in the space, in between. All right. Repelled by this side, attracted to that side. What's true about the total energy of that electron as it moves?
It increases.
It increases? Is that what you said?
Yeah.
So I can put in a particle inside this thing and the energy of it increases? Why are you going with it increases?
I don't know.
You just felt right?
Yeah.
Okay. Anyone else? They want to back them up or just say, "Chow, come on."
I mean, I don't think Chow's right, but I don't know what the right answer would be, so.
Okay. Just out of sheer principle? Chow's not right.
Well, that and it just doesn't seem like a right answer as well.
Okay. Katie, you were about to say?
I was gonna say kinetic energy increasing, because it's moving.
All right, but the question was about total energy. So I'll agree, kinetic energy increases in the scenario I gave.
So does that mean total energy increases?
Pardon?
Does that mean total energy increases?
What are the two types of energy we're talking about here?
Oh,
Kinetic and potential.
Okay, so kinetic's increasing, I'll agree with that. What's happening to the potential?
it's decreasing.
So what's happening to the total?
Staying the same.
Well,
Yeah, it's constant. It's conservation of energy.
I was close.
Electric force, ultimately it's an electric force involved here. It's a conservative force. Energy is conserved. All right. So the work done in moving this thing, I'm not worrying about signs at the moment, but let's flash back to the work-energy relationships. The conservative work that is done is equal to the negative change in potential. The work done is going to be equal to the force times the displacement. And I'm just going to drop signs because we're going to think through those. So the magnitudes. So the work is just force times displacement. What is force? If I have an electric field here, how do I find the force?
The K, Q1, Q2 over R squared
And then
times
our
R hat.
Okay, so that's the force, but let's do it in terms of electric field. What's the relationship between force and the electric field that this electron, I've stuck this electron in? Into which I stuck this electron. We'll still see it after. Okay, it's still covered. The archaeologist will find it. The relationship between force and electric field. Indeed. Well, let's start out with writing the formula down for force for just two charges. So F is K sub C or E, Q1, Q2, over R squared. What's the formula for electric field?
okay, so that E or C, the
It's either one. I can flip back and forth.
Q1 divided by R squared. R hat 2.
If that's Q1, that'd be R hat 1. So how do you get from force down to electric field? What did we do?
Divide by
You
Yeah, we
divide
did.
it by one of the forces, the charges.
Yeah, we divided by a charge. So if I take the force, the electric force, on 1 from 2, and I divide by charge 1, I get the electric field produced by 2. Or, in something that's a little bit better, a bit more visible, the force, the electric force on particle 1 because of particle 2 is equal to the charge of particle 1 times the electric field produced by particle 2. In other words, force is just the charge of this electron times the electric field that it's in. So this will be Q times that electric field dot delta X is equal to delta U. The signs are bugging me, so I'm just putting absolute value symbols around it. If I divide both sides by the charge, I get the electric field times delta X is equal to delta U divided by Q. And what is the change in potential energy divided by a charge?
The electric potential.
Close.
Energy.
Farther. It changed in electric potential energy.
Voltage.
Thanks really on both sides. So what we have here is a relationship between the voltage between the plates, the electric field, and the distance between them. So if I say the distance between them is the distance d, ignoring signs, my voltage should be the electric field times the distance between them, ignoring sign. I like to think of this equation as the ED equation, or VED. So if my electric field is Q divided by A over epsilon naught, then my voltage between them should be, well, that times the distance. Q D over A epsilon sub naught. And in this particular case, I know what the voltage is. So if I just gave you a little bit other information about the construction of this, you could calculate what the charge is. So let's just go ahead and do that. So let's say that the distance here is 0.001 meters, and the plates are 10 meters by 10